Welcome, everybody. We have the session in regression models this afternoon, and we have a distinguished set of speakers, Tobias, Hannah, Ahim, and Pierre, and we're going to get started. What I ask everybody is for your questions, put them in chat. We are going to reserve, if there is time allotted, to answer those questions at the end of each talk. If there is some technical issues, I will intervene, but I will remain myself in mute, and I will just give 1 minute a prompt when your time is about to end. So, Tobias, if you want to take it off, thank you very much.
Yes, I will. Thank you. So now you should see my slides, right? All right.
Yes.
So first of all, thanks for having me. And in the next couple of minutes, I'm going to talk about the ROB survey package. Then robustness means here that the methods are resistant to outliers, and our focus is on survey methods, that is on stratified samples or more complex samples. This is joint work with Beat Holliger. And in this talk, I'm going to give you an insights about two topics: basic robust estimators and robust regression. And I'm going to pick here a pen. There are certain requirements. Obviously, we need the ROB survey package, and if we choose the option quietly true, then that startup message isn't shown. We use two data sets, the loss data and the counties data. Let's start with part number 1 on basic robust estimators. Let us start with the loss data. Loss, that stands for length of stay in hospital. It's measured in days per year. Here we have a sample of 71 patients, and that is from a hospital population. We have the loss variable. First individual was 10 days in hospital. We have sampling weights, and we have here the last variable, FPC, that's the population size. That is used for finite population correction. The distribution of the loss variable, we have an average of 13 days, and we can see from this box plot here that are a couple of outliers. There's that unfortunate guy here who was 182 days in hospital, which is clearly an outlier. Not necessarily an error, but an outlier. And also perhaps this second one. In the next couple of minutes, we're going to look at more robust estimators, which may incur some bias, but overall may be more efficient. These estimators come in two flavors, namely the bare-bone functions and the survey methods. The bare-bone functions are called weighted mean or weighted total, and then followed by winsorized or k-winsorized, trimmed, Huber, Tukey. These are the M estimators, or underlined Dahlen. That's Dahlen's estimator, which is on censoring value and weight. So for instance, weighted mean winsorized, that's the bare-bone function for the winsorized mean. We also have the survey methods. They are called survey mean or survey total, and also followed by one of the suffixes here. Pretty obvious, I think. Next, let's stick with the bare-bone functions, and suppose I want to compute the 2% one-sided winsorized trimmed weighted mean. First, I attach my data, then I compute weighted mean winsorized of the length of loss variable. I lost here the picture, now it's back, okay, and the weight variable. In addition, I specify LB, that stands for lower bound, and UB, that stands for upper bound. Lower bound 0, that means we have no winsorization at the at the bottom of our distribution. And upper bound 0.98, that means that the largest 2% of the observations are winsorized. The return value of all the bare-bone functions is just the plain number here, as the estimate, a scalar. So you can see it's a pretty lightweight or minimalistic bare-bone function. It may be useful for package developers. The survey methods are much more capable. In particular, we can use them to compute variances. First of all, I load the survey package. Then I define a survey design object. That design object is then used, what we call survey mean winsorized, for the variable loss, which is defined in terms of a formula. There goes that survey design object. And again, we have LB and UB. Now we can see the return is a more complex object. In particular, we have here the standard error. And this is computed with the functionality of the survey package, the package by Thomas Lumley. The return value is actually an instance of the class survey.stat_rob. And for this class, we have a whole bunch of utility methods. We have coef for coefficients, variance coefficient, covariance matrix SC. These are the standard utility methods that are also available in the survey package. Rob survey defines a bunch of additional functions like summary to give a summary, MSE to compute the mean squared error. Residuals and fitted are pretty obvious. They are very well known from linear models. The last two functions, rob weights and scale, they are only useful or can only be used for M estimators. Next. What more? Well, all the functions are implemented in the C language. And for the two M estimators, namely the one with the Huber and the other one with the Tukey psi function, well, in addition to these functions, we provide an interface in order to add support for additional psi functions. And we document how to do that. More importantly, have a look at the vignettes. There we treat all the estimators in more detail. There is a vignette on basic robust estimators, and there's another one on the robust Horwitz-Thompson estimator. Next, in part number 2, I'm going to look at robust weighted regression. First, we start again with a data set. I have here a simple random sample of size 100 counties in the United States. The population of the counties is roughly 3,200. The data are from a famous sampling book, the book by Sharon Lohr. I only display here the most important variables, well, county and farm pop. Farm pop, that's the farm population. The second variable of interest is num farm, the number of farms in that county. We also have weights and population size. Next, I'm interested in the following model. We want to regress farm pop on num farm, as it is shown here in this scatter plot. From there, we can see that the variance is not constant, so there is heteroscedasticity. And I'm going to assume that the variance can be described or modeled by the square root of num farm. We also need a sampling design, and more important, we're going to fit the model by weighted least squares. The function to do so is called survey reg for survey regression. First, I define the formula, then goes my design object, and the last argument here is the heteroscedastic variance. The output, well, there's a title, then here we mimic the output of the linear model function, and last, we also display the estimated scale. Next, there is a whole bunch of utility methods available, like coef, residuals, fitted, plot, and so on. Next, we want to talk about inference. Inference on the following linear model, where theta is kind of special here in this application because we have in total, so to speak, 3 different thetas. We have theta here, that is the superpopulation model. Theta n, that is the census parameter or the finite population parameter that is used to define the model in our population. Well, both of them are unknown to us. What is known is the sample-based estimator, because that's the guy we actually can compute, theta hat n. Now we can think of this estimator that it estimates, say here, the census parameter. Then we are interested in what is called design-based inference. So the goal is, or the target is, theta capital N. To do so, we then choose in the summary methods or in the VCOF methods the mode design. If, on the other hand, we want to estimate the superpopulation parameter theta, well, then we have two choices. First one is a model-based. So that is our goal or target is theta. We ignore the sampling design. We can do so by choosing mode equal to model, insert in summary and weak-off. If we are interested in the compound design model distribution, well, then we choose in those functions mode equal to compound. I cannot go into the details here, but have a look at the literature given here. There it is discussed when it can be advantage or when it can be beneficial to go into the compound designed model distribution. So now we're ready to go into robust regression. We stick with the same data set, but this time I want to use a log-log model. The variance here is more or less homoscedastic, right? But taking the logs on both axes, well, then it appears this outlier here. So therefore, we want to go into robust regression. Yes, obviously, we are not the first to handle or to deal with robust regression. There is a ton of other implementations. They are given, say, in MATLAB, in Stata, there is the GNU Scientific Library in C, and so on and so on, a lot of R packages. Here, I distinguish two parts. The first entries are with some kind of weighting. The second part of the or tabulated packages and tools is without weighting. We can see here that the M estimator of regression, that's available everywhere. Our focus is on GM, generalized M estimators. There are implementations without weighting in the ROB-ETH library and NAG, that's numerical algorithms group, their C and Fortran library has it implemented. So our contribution is bring all sorts of weighting into GM estimators. So focus is on GM, on M and GM estimators. The function is survey-rec, and again, we construct the functions by either following Huber M for the M estimator or Huber GM for the GM estimator. The first argument is the formula, the second the design. Then we have K. K is the robustness tuning constant for the Huber psi function. For the GM estimator, we have in addition the arguments type and X weight. Type defines what GM estimator we actually want. We can choose between Mallows and Schweppe. X weight, that's the argument where our weights go in order to downweight high leverage observations. In addition, we also have survey-rec, Tukey M, and Tukey GM. These are the M and GM estimator with the Tukey psi function. We also have the very same utility methods I discussed some minutes ago, namely coef, plot, residual, and so on. In terms of inference, we also distinguish the three modes: design-based, model-based, and compound design model-based. Have a look at this vignette where we go into all the details. So let me come to my summary and short outlook. I showed you only a handful of functions. In total, there are 52 exported functions and also a whole list of S3 methods. For instance, we have a robust generalized regression, that is a GREG estimator, that comes up in model-assisted estimation techniques. We have a Tukey's weighted line, and so on. The most important takeaway message for you guys is the functions are available in two flavors: bare-bone functions and the survey methods, which are, I repeat myself, much more capable. In particular, they can be used to compute variances. Let me ask you, what is missing? What methods do you need? You can find this slide deck on the platform here, or you can navigate over CRAN to ROB Survey. There you'll find the link to my GitHub repo. And there in the following folder in stock, you can find all the details. I'm ready to take your questions, and thank you.
Thank you, Tobias. We don't have any questions so far. So
Okay.
if anybody has any questions, they can put it in the chat and either I can read them or I don't know if you have access to the chat, Tobias, but
I can barely see it on my small screen.
yeah, it's small. I was going to ask you while we wait for other questions, how hard was to build the package on top of the survey package? I know the survey package, is it quite extendable to do what you are trying to do?
Yeah, good question. Well, actually, in the current version, we only provide support for more or less classical designs. What I mean with that is Thomas Lumley has implemented also resampling designs and other more, let's call them exotic designs. They are not supported currently in our implementation. So there is still some work to do. And I hope that we will be able to add these functionalities in the next couple of months or even years.
I have another question. Is the survey package allows for likelihood fitting, and it at times I have used it to through the help of discussion boards and even through Thomas if to fit, for example, a negative binomial, which is not off the hand available. Are some of those options or requirements of more, as you mentioned, esoteric or not off the shelf models available?
What I meant is actually the type of survey design. And there, the
I
survey
got you.
package offers really a lot. And our extension, so to speak, ROP survey, only supports a rather limited number of functions. But in our package, we've only focused on the robust linear model. So we did not go into generalized linear models. So it's,
Okay.
so to speak, rather limited from this perspective.
Okay. Okay, I think a question came through, and thanks for the talks. Does the survey support GLMMS models, or is the support planned? I think they mean mixed models, which you just answered about the generalized. The question is about the mixed.
Yeah, I don't know, because I'm not into the generalized linear mixed models. That's not my business. So unfortunately, I cannot answer
Yeah,
that. But I think you
yeah.
can
I
regulate
actually
the
think
comments
sometimes the
from me.
survey is a way to account for those nestings.
I don't know. We have to
So
ask Thomas Lumley.
yeah,
That's not my
there is one
expertise.
more
Sorry.
questions in the last minute that you have. I'm curious to know whether your package uses mass and just added to for the GM feature, or did you rebuild from the ground up?
Thanks. Yes, it's rebuilt from the ground up. So, and we try to be sometimes close to mass, and sometimes we have to deviate from that. For instance, in mass, we have RLM, that's the robust linear model there. And they use the median absolute deviation as an estimate of scale. But they do not compute the median absolute deviation about the median. So they assume that it is that the residual is 0 or centered at 0. There we are a bit more general in the sense that we do not go for that assumption. And yes, it's built from ground up.
Okay, thank you very much, Tobias. Is Hannah's turn. Hannah, if you want to share your screen, thank you very much.
Hello. Does this look good for everybody? Excellent.
Looks perfect.
Hi, my name is Hannah Frick. I'm a software engineer at our studio on the Tidy Models team, and what I'm here to talk about is a package called Censored. The jokes write themselves, basically. It is a Tidy Models package for survival models. And if you attended Julia Selge's keynote yesterday, you have heard quite a bit of Tidy Models. If you have not, it is a framework for modeling and machine learning using tidyverse principles. And we are currently working on extending support for survival analysis in Tidy Models. Our first milestone is being able to fit and predict with survival models. So that is what Censored is about. And what we wanted to do with it was to make predictive survival modeling with existing packages a bit easier. In particular, we want to be able to switch more easily between different types of models, and we want to be able to easily compute on the predictions. So we're not rewriting modeling packages. We used the great packages that are already available, and instead bring a unifying layer on top of them to make those two aspects easier. These ideas are also embedded in the design of the Parsnip package, which is sort of the heart of fitting and specifying models in the Tidy Models ecosystem. So unsurprisingly, Censored is a Parsnip extension package for survival models in this term. There are others for linear mixed effects models, bagged models, various things. And now there's one for survival models. So let's dive a bit deeper into these two aspects. And I'll talk a little bit about Parsnip because that sort of sets the ground rules for what Censored is doing. And the idea is to give you a consistent interface across different models, because if you're going from one model type to another in a different implementation, you probably would like to be able to focus on the modeling aspects rather than to remember or look up the syntax that you need. That includes which functions, how to use them, what are the argument names, like if you're working with tree-based models, and the name of the parameter changes for how many trees are in your ensemble or how many observations do you need at least in each node. That's like not the main focus what you're there for, so we make those consistent. And we also apply some consistency to the format of the predictions that you get back. I'll talk about this a bit in the second aspect, but the TLDR of that is you get tables with unsurprising names and unsurprising dimensions. So about that interface, Parsnip relies on a full model specification consisting of three main parts. The one is the model type. That could be a linear model, a random forest, like in my example code on the right, support vector machines, a whole host of other things. The second element is what we call the computational engine. That might be a specific R package or tools even outside of R, like Keras or Stan. So here for my random forest, I've chosen the Ranger package. And the third aspect is the mode, such as regression or classification, that gives this model specification some context in what it is supposed to do. And these three elements are central to like Parsnip model specifications, and they reappear in Censored. What we've added specifically for survival analysis here is a new model type, proportional hazards, so you can fit your beloved Cox model, and a new mode. In addition to regression and classification, there is also censored regression to distinguish that. And Censored comes with a formula interface for all its models. Most of the packages that we've used as engines do that already, and we provide one for Glimnet. And the formula interface is also how you can specify stratification if that applies. And we give you predict methods for all of these models, which is probably very unsurprising. So to show you what is actually in Censored available, These are the engines that are in censored for the various types. They are all for the mode censored regression. So as I said, a new model type proportional hazards with survival and GlimNet packages as the engines. Parametric survival models can be fitted through survival reg. And then you have several different tree-based methods, models that already existed in the parsnip and extension packages, and now they're engines for this new mode, and they are located in censored. So let's apply some of these to some data. I got some citations for you today. These are dolphins and whales living in captivity in the USA. This is adapted from a Tidy Tuesday dataset from 2018. And the response is the age, how long these dolphins or whales lived or have been living. The event variable tells you whether they already died, sadly, or whether they're still alive, and a couple of other ones, species, sex, where they're located, where they're originally from, how many transfers they've had between different locations, and so on. So let's go with the proportional hazards model, since it's such a classical survival model. We need proportional hazards to function. We need an engine. I'm going to go with the survival package. And we need the mode, which is censored regression here. And we can fit this with the fit function, giving it a formula specification of the model and the data set. And if we want to add stratification, we're doing this in the same way that you would know from the survival package, which is to add a strata term into your formula. This is relatively verbose, and if you're used to working with the survival package, you know this a little bit more concisely like this, which is nice. However, this gets a little bit more frictionsome if you decide that a Cox model is nice, but you want to try out a penalized version of this. That is not in the survival package, that is in GlimNet. And GlimNet does not have a formula interface. You have to prepare your data for the matrix interface of it. So that's not just a case of pulling out the columns of your data frame and saying yes matrix on it. If you have categorical variables like I here with species and sex, you still need to turn those into dummy variables. And your response is also not just a column, that's the serve object that you've already seen. And if you want to stratify all of that, you have to stratify the response with GlimNet's own stratify serve function. And then you can give that to GlimNet, set the family to Cox, and set the penalty parameter lambda to a value. If you want to do this transition between the two models via censored, there isn't all that much that changes, which is sort of the main idea, obviously. So we have the proportional hazards function, and then for GlimNet we set a penalty parameter. But the main thing that changes is the line that says set engine, where we switch out survival for GlimNet, and then we set the mode. That is the same, and the fit function is the same. This looks very boring, and I'm quite happy about that, because behind the scenes, what this does for you is prepare your data for the right, in the right shape that GlimNet wants it. So all of the dummy variables and matrix transformations and all of pulling out the stratification variable and then stratifying your response, that is what's happening behind the scenes. But you don't need to care about that. You can just remember that all you actually really change is the set engine line. And if you then decide to give a tree-based model a go, this looks still similar. The thing that changes is the type of the model. Here it is a boosted tree, and the engine, for which here we use the mboost package. So that's this part. And I'll tell you a bit about the predictions. So predictions that you get from parsnip have like 3 characteristics. They're always in a table. The column names and types and dimensions are unsurprising and predictable, including the number of rows in new data and the output are the same. So if you have missing values, they're not being dropped somewhere along the lines, and you have to like pad your results. We've added new prediction types for this. So these are just the first 3 observations of the citations data set. To spice things up, I've added an NA. You need to predict function, your model, your new data set, and a type. If you say type equals time, you get survival time. The result is a tibble. It has 3 rows because you put 3 rows in, and the NA is at the right place here. And the other prediction type we have is survival probability. That is with the type survival, and this gets calculated at a specific time point. So here I'm calculating the probability of survival for dolphins and whales at age 10, 15, 20, 40. And the result is, again, a tipple. It's got 3 lines, but we had 4 time points that we wanted the survival probability at. So what you get in each element of that list column is a tibble with those 2 bits of information. So if we pull them out, you will always get a little tibble that has a column .time and a column .pred_survival. And if you can't compute the probabilities because of NAs, it will say NA all the way through. So these are the 2 main prediction types, time and survival, and you get those for all of the models and engines in Censored. And depending on what the engine provides, you can also calculate the hazard or quantiles of the event time distribution or the linear predictor if your model has that. And yes, formats are boring and hopefully let you move on to calculations with the predictions if you choose to do so. And that is it. Censored.tidymodels.org is the package down page, and this is the lovely new hex for it. Thank you.
Thank you very much, Hannah. Let's see if we get some questions from the audience. Somebody make a comment that it looks quite elegant, like syntax. So, and I second that.
May I ask a question while we wait for some more comments? Hannah, you mentioned that you use tibbles, so lists of tibbles where necessary. Could you maybe expand on what it took to decide that this is necessary, as opposed to using some other outputs to wide output? I mean, you cannot make it longer because that was your fundamental design principle. But what about making it wider?
I think that makes it a little bit harder down the line. Sort of the rest of tidy models building on tidyverse principles likes to have data in like a long format. So here, this one, if you just wanted to make it really long, you can just unnest it. Going to wider gives you more miles you still need to cover in order to then go and calculate performance metrics on these, for example.
So we have a question for the audience asking, do we get survival metrics as well?
You do down the line. So this is the first part, as I said, and there are no survival specific metrics in Yardstick. Yardstick is extensible, so if you have something you want to get working now, then you could do that. Once we have that, that will then unlock more. So you can already use workflows with it, but tuning does not work on these because what you're going to tune if you don't have a performance metrics. But that's sort of the direction that we're heading, and this is where we're at right now.
Good. The last question here, if you have an extra minute, Hannah, is less specific to the sensor package. I'm wondering how flexible is Tidy Models in its incorporating new packages. It just left the question.
We do
such
have
as Rob's survey, as they put it there.
Yeah. So the framework is extensible, hence the extension packages to Parsnip for specific parts. We do have documentation on tidymodels.org in how to do that if you're keen to do that yourself. If you would like us to take a look at extending anything, the best way is to open an issue on the Parsnip repo, I would say, making a suggestion, telling us what you need, why, any good implementations for it, and we'll take a look.
Okay, thank you very much, Hannah. Great presentation. So next is Ahim, and take it away.
Thanks. Just sharing my slides. Okay, thank you very much for the introduction. I'm very happy to be part of the session, also to be speaking after Hannah, because I will be touching on a few points that are related to what Hannah said, and maybe we can discuss them a little bit later. So I'm presenting this package, Distributions 3, and I want to show you how you can use that for basic probability, especially in a teaching statistics context, and what is probably of more interest for this particular session, to use it for probabilistic regression to complement certain tools. As we just heard, my name is Achim Zeileis. This is joint work together with our former postdoc, Moritz Lang. We both come from Universität Innsbruck, and Alex Hayes, who started the Distributions 3 project about 3 years ago. And to give you a little bit more background of what the package does, Alex designed it in the beginning, especially for teaching statistics. And the focus was to have these probability distributions as 3 objects. That's the object orientation system that is also used for data frames or linear models in base R. And an important goal from very early on was to make it beginner-friendly and well-documented and rather lightweight so that students could easily adopt it. And it saw quite a few early on contributions from Ralph Muller-Train, Daniel Jordan, Paul Northrop, and a few other people that joined the effort. Moritz and myself came in quite a bit later, more recently. And we came from a rather different angle. We were interested in the topic of assessing goodness of fit of probabilistic regression models. And we had an interest in extending these distribution objects to vectors of distributions, so that when you get a prediction, you can actually, for every observation in your data frame, get a full predicted distribution. And that's where we joined with Alex and co in Distributions 3. So the design of the package is relatively straightforward. There are class constructors for many of the standard distributions, normal, Poisson, binomial, and so on. At the moment, we haven't got any censored distributions yet, but I will be working on that in the next month. And these class constructor functions return S3 objects. And essentially, these are data frames, albeit with a different class. So you don't recognize them as data frames right away. And the variables in these data frames are the parameters of the distribution. So for a normal distribution, for example, you have one variable mu for the mean and another variable sigma for the standard deviation. And you can then have a single row in the data frame corresponding to just a single normal distribution, or you can have several rows corresponding to a vector of distributions with potentially different parameters. And then you have S3 methods operating on these objects and performing certain standard tasks you want to do with distributions. So you can extract the mean, the variance, quantiles, evaluate the probability density function, cumulative distribution function, simulate random variables, and so on. And you might say, well, we have all of that in base R for the standard distributions. We have these common dpqr functions for density, probability, quantile, and random values from the distributions. And this is, of course, correct. And we do use these functions under the hood. But the point is that you create the object once, and after that, you don't have to care about which specific D or P function you need to use, whether it's the norm or the binorm, because this is encapsulated in the class information. So to illustrate this with a basic example, we create a Poisson distribution here for count data. And when you introduce that in an introductory statistics class, you might say, well, we have a distribution with support on the non-negative integers and characterized by a parameter that gives you the mean and coincidentally also the variance of this distribution. And this is the probability mass function. And then you might go on to give some illustrations, what the distribution looks like. And say, for illustration, we can use a Poisson distribution with a parameter of 1.5. Well, in distributions 3, after loading the package, you can do essentially exactly the same. You just say y gets a Poisson distribution with lambda 1.5. And then you can print that, and you can evaluate this probability density or probability mass function at the counts from 0 to 5, giving you the resulting probabilities. And you can do more. You can extract moments, mean and variance, both 1.5 in this case. You can evaluate other functions like the CDF to give you cumulative probabilities. You can get quantiles, and you can simulate random numbers. And the nice thing is, you don't need to care about what kind of distribution y is, because these functions always do the same thing and behave in the same way, giving you these quantities you might be interested in. So to add a little bit more meat to this, let's look at an example which we could use in the classroom. And I'm analyzing here goals scored by the 2 teams in every one of the 64 matches in the 2018 FIFA World Cup. So that's football or soccer. And we have this data frame in the package, and I will be first mostly, interested in this goals variable only. And for every match, we have 2 goals. So the opening match was Russia against Saudi Arabia, which Russia won 5-0. And we have a few standard covariates for the type of match and so on. And a little bit later, we will use this variable, the log ability, which is a prediction based on bookmakers' odds of the different team strength, if you want. But I'll come back to that in a second. Let's first do something simple, and let's assume that all teams have the same strength, and we just fit a single Poisson distribution to this data set, and then the maximum likelihood estimate for the lambda parameter is just the mean of the goals, which is around about 1.3 in this tournament. And then we can create a Poisson distribution with this, and we just have one single Poisson distribution from the entire data set. Rather than computing the MLE by hand using the mean, you can also fit a simple constant distribution with a fit MLE function in the package. Or you could use a GLM with just a constant, but I'll come back to that in a moment. And then to see whether this really fits the data, we might want to compare observed and expected frequencies. So we take a table of the goals, turn it into proportions, and then compare this with a PDF of this constant fit Poisson model on the counts or goals from 1 to 6. And we can row bind these together, turn them into percentages to make it a little bit easier to read, and maybe compare them graphically. That's a bit easier. And here we see that the observed frequencies, dark gray, and the expected frequencies from the single Poisson distribution in light gray more or less conform with each other. So it's a pretty okay fit. But we might want to go beyond this, obviously, because not all of the teams have the same strength and they will have different abilities, which is why we want to use this predictor based on the bookmaker's odds we have for this data frame. And the idea is to set up a regression model now. So we're moving from the simple constant fit to a Poisson regression now. And we want to explain the number of goals per team by the ability difference, with the idea being that your team will score more goals if the difference to the ability of the other team is greater, or you will score less if it is less. And we can do so with a basic GLM function, modeling goals by the difference, taking the FIFA data, and fitting a Poisson model. And the result is assigned to a model object M. And we could look at the summary, but to make it a bit easier to read, I just extracted the coefficient test table here. And the main interest is in the row for the difference. So we see that indeed we have a positive effect, that the higher the difference, the more goals the stronger team scores. And this effect is also clearly significant. And now we can also move beyond the simple regression interpretation with the coefficients and the means and actually move to a probabilistic prediction. And we now have a fitted mean for every single observation, which is typically different. And every one of these is actually associated with a full probability distribution. So we can wrap this in Poisson again, and we get back a vector of Poisson distributions with 128 elements, same as our data frame to start with. And we actually have a convenience function for extracting this probability distribution, PRODIST, from the model object. And you can also feed in a new data argument if you want to do an out-of-sample prediction. That's also possible. And this opens up all sorts of opportunities for unified and simplified predictions and computations more generally. These might be domain specific here. We could look at probabilities for certain match results, how likely it is to get a 1-1 or 2-2 or 2-1 and so on, or the probabilities for win, draw, and lose. Or we could also work on a more refined model so that we get a better prediction of the expected goals. So all of this is in principle possible. But here, in the last few minutes, I want to show you something different. I want to show you how we can leverage these probability distributions for general probabilistic modeling, scoring, and goodness of fit assessments. So the question that Moritz and I wanted to answer was, for models like this, not only GLMs, but more general probabilistic models as well, is how well is the model calibrated? And one possible idea, among various others, is to compare the observed and expected frequencies again. So we can go back to our PDF now for this whole vector of Poisson distributions, evaluated again on the counts from 0 to 6. And then we get a 128 by 7 matrix. And for example, we can see that Russia was a lot less likely to score no goal compared to Saudi Arabia in this starting game, 17% versus 42%. And to see how well on average the Poisson model fits, we now compute the column means of this matrix. And we visualize observed and expected frequencies again, but now using a square root scale, which makes it a little bit easier to compare the high and low frequencies. This is also known as a rootogram. And here I do this thing in base R. I just use bar plot and I now use the square root of observed, and afterwards I add the square root of expected, and I do a few further tricks to get this fitted line of the expected frequencies, and then I hang the bars for the observed frequencies from the expected frequencies. The advantage is that we see the deviations along the x-axis. And here the impression is that we get a few deviations, but they are not too huge, and by and large the model fits quite well. And this is now the thing that we put into our other package, into the top models package, and we have a rootogram function, which behind the scenes essentially does the same thing. It extracts the probability distribution, does the standard PDF computation, and then draws the rootogram. And you see that these are essentially the same. We add some nice confidence intervals here, but otherwise it's very similar. And if you prefer ggplot2 graphics, so this is base, you can just load the ggplot2 package, and then by default, rootogram will draw a ggplot2 plot. Of course, you can ask specifically which one you want, but by default, it makes this decision for you. And there are other visualizations that work in the very same way. Based on these general distributions we analyze, you can get pit histograms, randomized quantile residual, QQ plots, worm plots, reliograms, and so on, all in this unified object-oriented way. Where do we go from here? In distributions 3, we want support for more distributions. I already mentioned censored distributions and more models, which is starting here. And then top models can leverage the full strength of distributions 3. We need to do some polishing up and finishing our introductory vignettes. Then we'll put the package on CRAN. One thing I'm particularly interested in, I promised it in the abstract, but didn't get around to it yet. I want to interface more scoring rules from the scoring rules package. If you're interested to learn more, you can look at the package down web pages of the two packages on GitHub for distributions 3, on RForge for top models, or you can reach out to me on Twitter and find more information on my webpage. The PDF slides are also shared on my webpage. I can post the link in a second. Thank you very much.
Thank you, Achim. That was a fantastic talk. And I would like to remind you the famous quote. You know, you do a lot of statistics, but I think it was this famous soccer player, Gary Lineker, which says, football is a simple game, 22 men chase the ball for 90 minutes, and the Germans always win. So,
except in 2018.
Yeah. And to the chagrin of Argentina. So several times. We don't have any questions. Maybe wait a minute to see if there is any questions.
And then maybe I add a comment, possibly most for Hannah. In top models, which I didn't talk about that much, we also have this companion function that based on the raw distribution models that we then want to make unified probabilistic predictions, where you also have the safety of, by default, always getting a data frame with the same number of rows, and then you can ask for quantiles, probabilities, and so on. So rather than doing these steps yourself, there's also a wrapper function that does this in a consistent way. But the focus is always on probabilistic forecasts and not so much on mean regression or classification.
Yeah, my only comment is I find that the package to be very unifying in the type of things you can do. Oftentimes, if you need to do a simulation, you need to learn distribution, you need to learn a special way of doing that versus if you do it this way, it seems pre-unified. So maybe we will reserve a question at the end, but we are going to let Pierre go next. Pierre, if you want, just take it away.
Thank you. Okay, so can everybody see it well? Okay, so good afternoon / evening, everybody. I am Pierre Masselot. I'm a research fellow in statistics and environmental epidemiology at the London School of Hygiene and Tropical Medicine. And I will present quite a simple package that we are currently working on with my colleague Antonio Gasparini, which is called CIRLS for Constrained Iterative Reweighted Least Squares, that allows to do constrained estimations in GLMs. So basically, the problem that we wanted to solve is as follows. So you recognize on the top line a classical generalized linear model. And here, what we want to do is to fit this model with some linear constraints on the coefficients beta. So these linear functions take this shape. We have a constraint matrix that gives the constraint, and lower and upper bounds for these constraints. So this means that these constraints can have any linear forms of the coefficients, and it's quite flexible given to the two bounds. It also includes the possibility of equality constraints when the two bounds are equal. So why would we want to do this? Well, there are several, a lot of potential applications. So a common application would be non-negative regression, where we want the coefficients to be positive. So for instance, when we want to estimate the risk of air pollutants on respiratory disease, we can assume that it is positive. And so we force the model to have these positive coefficients, which allows it to be robust for instance, rural areas where we don't have a lot of cases or a lot of data. This can be the case for compositions also. So compositions are when we have a range of variables that should always sum to the same value, so to 100%. So for instance, the composition of of particulate matter. So what is the effect on health? And in this case, we might want that the sum of our coefficient is null. Or we have also more complex cases, such as convex regression. So when we smooth using splines, for instance, we can impose some constraints on the coefficients of the spline to have specific shapes of our curve in the end, such as, for instance, if we want a convex curve, we put some constraints on the second difference of the coefficients. So how is it fitted? Well, we reuse the classical iterative reweighted least square algorithm that is used by default in GLM in R. And so just as a reminder, this algorithm iterates a least square fitting, weighted least square fittings, where we, instead of having directly the response, we have these weights, these pseudo weights, and pseudo response here, Z, that are changed at each time, at each step, depending on the current parameters. So here, what we do in this algorithm is that we replace this very simple least square by what we call a quadratic program. This is quite a general optimization technique that allows to minimize quadratic functions, so such as the least squares, given linear constraints. And so we can quite easily rewrite our least square to fit the quadratic programming framework. And so we just replace it, plug in there, and we can have, in the end, our estimates with constrained coefficients. And from there, we can also perform some inference on the estimated coefficients. So having these constraints, basically, it reduces the degrees of freedom in the regression. And so this tends to deflate the variance of the coefficients. And so we can show basically that a simple transformation on the coefficients using our constraint matrix here follows a truncated multivariate normal. So this is a multivariate normal distribution that is truncated at one or both ends. And we can simulate from this distribution to then obtain simulated coefficients from which we can compute variance covariance matrices or confidence interval just by computing empirical variance or quantiles on these simulated coefficients. But enough of the theory. How does the package work? So we thought the package as a plugin for the GLM function in base R, the very basic GLM function that probably most of you have used a million times. And so here I show the usage part of the help of the GLM function in package stats. And you can see that there is a possibility to provide a specific method to fit the GLM. And so we have written this function cirls.fit to replace this glm.fit in the method. And so we can directly call this function that will be called inside the GLM function. And in addition, we use the dots argument to pass to our function the additional parameters that we need. So specifically the constraint matrix and the lower and upper bounds of our constraint, and also a bunch of other parameters that help the fitting process. So this really allows us to kind of use the whole machinery of the GLM in the stats package. So this is how it looks when we call it. So for instance, we have here a simple model where I have this response called Y-norm, and I want to model it using these terms X and Z. Note that these terms can be also matrices. So for instance, if X and Z are basis functions from splines or Fourier components or anything else, these can be matrices. So call our function cirls.fit through method, and we can then pass the constraint matrix and, if necessary, lower and upper bounds here. So we have here what I call the full call, where we have to pass this constraint matrix fully specified, which means that it must fit the size of the model matrix. So this has to account for potential for the intercept and potentially the dichotomized factors in the model matrix. So this can be a bit cumbersome, but it's possible. The other possible is to pass CMAT through a list where we can give specific constraint matrix that will be applied on each term. So if we want constraints on specific terms only, we can pass it through list, and internally the function will create the full constraint matrix so that the user don't have to worry about that. And note that we can also pass, for instance, if we have only non-negative constraints, we can just give 0 to the lower bound, and internally it will be recycled as well. So it's a more convenient call for the function. So in the output, we also add an additional class to the output of this function. So by default, we have the class GLM and LM when we call GLM, and in our function we add this class CRLS that will allow us in the end to create alternative methods for this class. So in this case, for instance, we could create this new method for vcov and content that use the theory that I talked about earlier. But we keep the classes GLM and LM, which allow us to really use the whole existing machinery that is associated to GLM. So there is the print, summary, fitted functions. We didn't have to code them. They were already written and they can be used readily with our method, which was super convenient. So as an example of what we can do with it, here I used the Nmaps datasets that includes time series of daily mortality, mean temperature, ozone, PM10, and a few other exposures for 14, oh, it's 2000 here, for 14 years in the city of Chicago. Here we will focus on the summer, and here we will try to assess the effect of the various environmental exposures. So we will include O3, the ozone, and PM10 linearly into the model with non-negativity constraints, such as in the example I showed earlier. So we know that it's very unlikely that these pollutants would have protective effects. So it's reasonable to assume they will be the coefficients will be positive. And for Temin, since it is known that is usually quite strongly nonlinear, the effect on health, we here use a B-spline expansion with 10 bases. And we apply convexity constraints. So the constraint matrix would look like this. So here in this instance, it would look like this with 5 bases for the B-splines. Here in the results I will show, I used 10 bases. So this is a quite a simplified version of the constraint matrix. And we fit the quasi-Poisson model that account to over-dispersion that is usually observed in this kind of mortality data. So how do we fit it? We fit it like I showed previously. So we have the formula here with our various exposures, and I also included a term covariates for additional confounders. So in environmental epidemiology, in this kind of studies, it's commonplace to add, for instance, a term for the seasonality of the mortality and potentially an interannual trend, things like that. So here I put it in this single term covariates. So we call with a family quasi-Poisson and our method CRLS.fit. And so we can use this list of constraint matrices. So for Temin, it will be this matrix of second differences of our coefficient that I showed just before. And since we have only a single coefficient, it will be linear for PM10 and O3. We just have to provide one here. So it will be just a positive, it will be just a constraint on this single component, this single coefficient for each of these terms. And note that by default in the function, we have the lower bound to 0 and the upper bound to infinity. So no constraints on the upper bound. So this is why I didn't provide them here. We will keep this default in this case. And so we fit the model, and after that we can extract the coefficients. So for instance, here I show the relative risks by taking the exponential of this coefficient for O3 and PM10. So we see that we have rightly our positive coefficient. And we also see that here with our confint method, we have these confidence intervals that are always above 1. So since below 1 wouldn't be allowed, this confidence interval are always in the feasible region of the coefficients. And similarly for the relative risk of mean temperature. So we can extract here the variance covariance of the coefficients that are associated with the splines T-mean that can then be used to compute this confidence interval here through the splines. And so we have this nice convex curves that with increased risk for the highest temperatures. So I have a second example on the a data set that is plasma, where we want to estimate the effect of several covariates on the amount of beta carotene present in blood plasma in a bunch of patients. So here we will include in the model whether the patient smokes, the BMI, and we will put a constraint that it is a smooth function that is decreasing, and the effect of age, a smooth function that is increasing. And so, as for temperature previously, we model BMI and age through B-splines. And here I show the results. So in red are our curves that are estimated by the constraints model. And in gray are these curves that are estimated by a non-constrained model, which is by the classical GLM. And so you can see, for instance, that on the lower hand of the BMI, this function is very wiggly when it's not constrained, while here it's close to zero with the constrained model. And you can also observe, for instance, that where the constrained and the unconstrained curve match, the uncertainty is very similar, while, for instance, when they don't match, the uncertainty of the unconstrained model is greatly reduced. So this is an interesting thing of this constrained coefficients. So to summarize, this package provides a simple plugin for the GLM function to fit these constrained GLMs. So we want to take advantage of all that is existing in the stats package, all the methods such as the predict and the print methods. With this added class, we can also provide additional alternative, I should say, methods. And one thing that I didn't touch upon is that we had the possibility to use various solvers for the quadratic program that is at the center of the algorithm. So by default, I use the OSQP, that is a more recent and very fast solver, but there is also the quadprog solver in R that was probably the gold standard for a while. And there is also this conprog solver that is interesting so far. So the package has not made its way on CRAN yet. So you can find the development version on my GitHub at the following address. We are starting to write a manuscript as well to showcase the method and the package. And you can contact me either by email or through Twitter anytime if you have any question.
Okay, Pierre, you got a question. I want just to mention, because you have a minute and a half to answer that question before we have to close the session. I want to thank all the speakers before you answer. And I want to say that in the user program, there is the abstract of each talk, and all of you have links to your GitHub repo or your presentations. And I know I looked at some of them and a lot of the details are there. So the question for you was, did you compare the performance of SEALS, your package, to directly maximizing the likelihood under constraints? You have a minute.
It's not completely clear what would be the performance. So the idea of this constraint is that we kind of agree for potential loss of performance, let's say, to have a likelihood that is slightly lower, but for our coefficients to be more realistic. So we check that when our functions when the true function in simulations, for instance, respect our constraint, indeed this method is able to be closer to the true coefficients in this sense.
Thank you, Pierre. There is 15 minutes left. This was a pleasure. Thank you to all our speakers. There is a lot of work there. The presentations were super clear and the slides fantastic. So thank you again. Thank you for attending the USAR. Goodbye.